Hi, everybody. Welcome back to Dave's Math channel. This is my next video on my series on the Math Lovers book. This is a three-volume series available on Kindle and on in paperback on Amazon.com. You can search for it on Amazon.com. Either type my name, David Tare, or the title of the series, The Math Lovers book. There's three volumes. First two are kind of like textbooks. These the first two just kind of have. The first one's more recreational. That's the one I'm going over now. There's 10 chapters. I'm doing chapter 2 right now. But as soon as I finish that, I'll go over what's in volume 2, which is more academic and a little bit more advanced. And then third volume is problems and solutions. That has problems pertaining to the first two volumes as well as solutions, the odd numbered problems. And like I said, you can buy this on Amazon, and I talked about it in previous videos, so I'm not going to talk about it in detail in this one. But just suffices today that I'm doing a lecture series on the first two volumes of the Math Lovers book, and I'm up to chapter 2 of volume 1, which is on numbers, real numbers in particular, and or integers rather. And today I'm doing a sub I'm doing this I'm going over the section on prime numbers. That's section 2.2, and today I'm gonna go over Euclid's proof that there's infinitely many primes. That's not an obvious fact, but it is true. So let's begin. So here it is written out in detail in my book, but I'm not going to go over this slide because it's kind of long and I can't even read my writing at this scale. But what I did is here's kind of the whole theorem proved out a little bit more compactly. So here's the theorem. Euclid, around 300 BC, was able to prove that there's infinitely many primes. So how did he do that? Well, the proof is what's called an argument by contradiction. And by the way, I think I misspoke in my last video. I mentioned the fundamental theorem of arithmetic that says that every positive integer has unique prime factorization. This was also actually proved by Euclid. I didn't realize this when I was doing the video. I think I did mention it in my book, but pretty amazing accomplishment by Euclid in 300 BC. It's a very difficult proof, a lot more difficult than this one, that there's infinitely many. Once you know that every positive integer has a unique prime factorization, it turns out to be very easy to prove that there's infinitely many. So how do we do that? Like I said, this is an argument by contradiction. So the way arguments by contradiction go is you assume the opposite of what you're trying to prove. Let's just assume, for the sake of argument, there's only finitely many primes. Perfectly valid assumptions. I mean, primes do tend to get rarer, a little bit rarer as the numbers get larger. I think you kind of saw that in my last video when I applied the sieve of Eratosthenes to find all the primes up to 100. Turns out there's 25 primes up to 100. I think there's 168 primes up to 1,000. And there's something like, I don't know, 1,200 up to 10,000. I mean, the density goes down as the numbers get larger. So you might think there's only finitely many. But actually, Euclid proves it infinitely many. So let's just assume there's finitely many. Well, if there's finitely many, we should be able to list them all, right? So let's just make a list, P1, P2, up to Pn. And where these are listed from smallest to largest, like P1 is 2, P2 is 3, P3 is 5. This is actually standard notation for indicating which prime you're talking about. P25 is 97. That's the smallest prime less than 100. You can go on like that. But let's just assume there's finitely many. So then your last one would be p sub n for some integer n. So let's assume these are all the primes there are. And then what do we do? Well, let's take the product of all of them. So this is only finitely many. When you multiply them all together, you get a finite product. And now let's take that product and add 1 to it. And let's call that product, here they call it A. I think in my book I call it capital. And it doesn't really matter what you call it, but let's call it A. So A is some number, and it's the product of all the primes. We're assuming there's only finitely many, so A is the product of all the primes there are plus 1. Well, now what do? Let's try to factor A. And by the unique factorization theorem, it should have a unique factorization. So A should have a unique factorization as a product of primes. Well, suppose some prime P, let's just call it P, it's not one of the P's on our list. Well, we're going to prove it's not one of the P's on our list. So let's assume there's some prime P that divides A. Oh, no. How am I doing this? Oh yeah, let's just try to divide it by each prime. We have a complete list. Supposedly we have a complete list of all primes on this list. So let's just take any one of those primes. Let's just call it P. It doesn't really matter what we call it, but P is P sub I for some index I going from 1 to n. So let's try to divide A by P and see what happens. Well, since A is the product of all the primes plus 1, what that means, if you try to divide by A, you're going to end up with a remainder of 1 because the product of all primes is divisible by P. It's divisible by every prime. So when you add 1, you get a remainder of 1. Well, that's a contradiction. What that says is that none of the primes on our list can divide A because every one you try is going to leave a remainder of 1. So this is a proof by contradiction. That means that A, in reality, if we took some finite list of primes, maybe not all the primes, but we take any finite list of primes, multiple together, and add 1, we'll call that result A. What that means is that A has to have all of its prime factors that can have to be bigger than the biggest one on this list. None of them, well, a better way to say is that none of these primes are on the list we started with. So it wasn't a complete list because every prime on our list left a remainder of 1. That's the proof that there's infinitely many primes. And Euclid proved this around 300 BC. Pretty beautiful proof, I think. And I just say it in more words than this in my book. But anyway, that's Euclid's proof that there's infinitely many primes. And that completes my video for today. So thank you for watching. Long live math, and I'll see you guys next time.